In this lecture, we will conclude the vector review of vector algebra by solving a few problems. So, I am going to solve problem number 1, which is this figure shows a plane A, B, C formed by connecting three corners of a cube of side A. Show that the body diagonal shown is perpendicular to the plane. And the figure we are talking about is this cube of side A, and 3 points A, B, C are these A, B, and C, and the plane formed is this triangle ABC, and the body diagonal that we are talking about is going from this point to this point. And we want to show that this is perpendicular to this blue plane formed by these three lines A, B, B, C. For convenience, what I am going to do is take this axis to be the x axis, this axis to be the y axis, and this axis to be the z axis, and this corner to be the origin. Any plane you will recall is defined by two lines, right. So, we can take A B and B C, sorry, this is C, B C to be the two lines defining this plane, and we want to use vector algebra now. So, I will draw the plane, the cube and the plane again. This is the cube. This is the plane we are talking about A, B, C, A, B, C, and this is the diagonal, right. This is my origin, this is my x axis, this is my y axis, this is my z axis. So, the coordinates of A are nothing but A in direction x, 0 in direction y, and A in direction z. So, this is A 0 A. Coordinates of B are 0 in direction x, A in direction y, and A in direction z. Coordinates of C are 0 in direction z, but in x and y direction I have to move by A and A, and therefore, vector A B, recall from how we form vectors from the previous problem solving session, is going to be coordinates of B minus coordinates of A, and therefore, minus A I plus A j. Vector B C is going to be equal to C, coordinates of C minus coordinates of B, and this is going to be A I plus 0 j minus A k. So, I can write this as A I minus A k, and vector A C from A to C is going to be coordinates of C minus coordinates of A, and that is going to be 0 in the A minus A is 0, A j minus A k. So, these are the three vectors we formed. Now, the perpendicular to the plane A B C is going to be given by cross products of any of these three vectors. Remember, these vectors A B, B C form the plane A B C. Two vectors are enough to form plane A B C, and A B cross B C is going to be a vector perpendicular to the plane A B C, because A B C form a plane and cross product is always perpendicular to the plane formed by those two vectors. So, let us calculate A B cross B C. A B is nothing but minus A I plus A j, B C is nothing but, let us see what B C is. B C is nothing but A I minus A k, A I minus A k. So, A B cross B C is nothing but minus A I plus A j cross A I minus A k, which is equal to I cross I is 0, I cross k is minus j. So, minus A square j, j cross I is minus A square k, and j cross k is I, and therefore, this is minus A square I, which I can write as minus A square I plus j plus k. So, this vector A B cross B C is proportional to vector I plus j plus k. And how about the vector in the diagonal direction? Let us see that. Diagonal direction is from here, the origin, to this point. The coordinate of this point is nothing but A. So, this diagonal vector is nothing but A I plus A j plus A k, again proportional to I plus j plus k. So, notice A B cross B C was proportional to A I plus j plus k, although in the negative direction, that is okay, and the diagonal is in this direction, both are parallel. That immediately tells you that diagonal is perpendicular to the plane. Problem number 2. Figure shows, so let me draw the figure first. X, y, z shows a vector OA with projection on z axis OC and projection in xy plane OB. So, here is a vector OA and its projection on the z axis is OC and projection in the xy plane is OB. This is OB and this is OC. So, you can see immediately that OA is nothing but OB plus OC, because if this vector is transported parallel to itself, this is also OC. So, I am drawing these pictures so that your imagination in 3 dimensions becomes better and better. So, the problem is figure shows a vector OA with projection OC on the z axis and projection OB on the xy plane. Then show that OB is equal to minus k cross OA. This is what we are supposed to show. Let me give you a little idea about when we say projection. Always think of projection like this. Suppose I have this axis x y z and the vector OA. Think of light falling parallel to the xy plane on z along its projection or its component in the xy plane. So, better would be I will change the order. If I look at xyz and this vector OA, if I want to see its projection on the xy plane, think of light falling parallel to the z axis on this vector. Okay. Think of this vector as a stick. The shadow that this light makes in the xy plane, the shadow is going to be the projection in the xy plane. Next, think of light falling along this shadow perpendicular to the z axis. Then the shadow that it makes on the z axis is going to be the projection on the z axis. So, I am giving you a physical way of thinking how to think of these projections. Projections are nothing but shadows made if you think of that vector as a stick and let light come from other directions. So, first if you want to see the projection in the xy plane, let light come parallel to the z axis and the shadow in the xy plane gives you the projection on the xy plane, and then parallel to that shadow you shine light perpendicular to the z axis and the shadow it makes on the z axis is going to be the projection on the z axis. So, now back to the problem. The problem that we have is this. I have this vector OA and its projection in the xy plane. That is why you see I am drawing kind of light going down is OB, and its projection on the z axis, you see I am going parallel to this OB is OC, and I want to show that OB is equal to minus k cross OA. Now, you see if you notice OB magnitude, right, if this angle from the z axis is theta, OB magnitude is going to be nothing but OA magnitude times sine of theta. Let me explain that a little better. Look at this plane, look at the plane OABC. Let me draw this plane for you. This is my plane O, A, C and B. This is projection O B, this is projection O C. You see what I am trying to do is to visualize things better, I am trying to draw a two dimensional figure. So, I have drawn this figure OABC and this is my vector OA. This angle is given to be theta. So, you can immediately see that if I look at this triangle OAB, this is nothing but OA magnitude. So, this should be magnitude sine of theta. Okay. So, this by definition is nothing but k cross A magnitude, because this vector is k unit vector. K cross A is going to be nothing but A mod of k mod of OA sin theta. Mod of k is 1. So, this is nothing but modulus of k cross A. Notice if I apply my right hand rule k cross A, right, k cross A in this plane, I turn my fingers from k to a, and this is going to be k cross a going into the plane of this paper. So, its magnitude of k cross a is all right, it is O A sin theta, but its direction is perpendicular to the plane O B A C. I want to bring it back to O B. So, if I take k cross a, k cross a I have already shown right here, I am turning my pen around here, is going into the page. So, if I turn my fingers from k to into the page, I get a vector in this direction. I want to switch it to the other side, I better put a minus sign here to the left of the screen. So, minus k cross a is parallel to O B, and the magnitude of k cross a is nothing but magnitude of O B, because this is nothing but O A sin theta, and therefore, it is immediately clear that O B, this implies that O B is in the direction of minus k cross a and has the right magnitude, and so this is proved. This also then tells you, again let me make this picture, this is my vector O A, I am throwing light parallel to the z axis. So, this becomes O B, I am throwing light parallel to this projection, this becomes O C. O C is nothing but k dot a, right. This is nothing but O A sin theta in the direction k, and O B we have just shown is nothing but minus k cross a, and O A is nothing but O B plus O C. So, a vector O A is nothing but minus k cross a plus k dot a k. A generalization of this problem, I can now generalize this. If I have a vector A and a unit vector n, then the vector A is equal to n dot A n, that is, if I take the projection of A in the direction of n multiplied by n minus n cross A. I will leave this for you to prove. I will give you hints. So, again if I have a unit vector n A, then n dot A is component in the direction of n. N cross A is nothing but, if this angle is theta, its magnitude is nothing but magnitude of A sin theta, right. This is the projection perpendicular to n, and n cross A is going to be in the direction perpendicular to the plane formed by n and A. I have to bring it back in the direction of projection of A in the plane perpendicular to n, and you use the same trick as we did earlier. This concludes our review of vectors. I will be given an assignment on this on this topic soon.